Hello, I'm Agnur Karabay, Research Assistant at the Institute of Smart Systems and Artificial Intelligence, and in this video we'll cover K-nearest neighbors classification. To begin with, let's recap the definition of supervised learning. Well, supervised learning is one of the machine learning types where labeled data are used to learn a mapping from input features to output labels. One of the commonly used supervised learning algorithms is K-nearest neighbors. It is used to solve both regression and classification problems. In general, KNN identifies the class or value of a new sample based on its proximity to the labeled data samples. To understand the KNN algorithm, let's consider the data points shown on this plot. We have three different classes represented by colors of red, green, and blue. Now we need to identify the class of unknown data point X. In KNN, we can infer the class of this sample point X based on its nearest neighbors. Well, let's consider four nearest neighbors, k equal to 4. So within the dashed circle, we see four closest nearest neighbors, from which 3 of class blue and 1 of class green. Consequently, the class of X will be inferred by the majority vote of its four nearest neighbors, which will result in blue class. There are two main hyperparameters in KNN algorithm. The first one is number of nearest neighbors k, which is used for majority voting. And the second one is distance metric, which is used to measure distance between data points. Well, how to choose the number of nearest neighbors k? Let's consider this plot. If we choose k equal to 5, X will belong to green class, since we have 2 blue versus 3 green within the dashed circle. And if we consider 9 nearest neighbors, X will belong to blue class, since we have 6 blue versus 4 green. Low k makes the algorithm unstable, whereas large k makes it more robust but computationally expensive. Usually, during the majority voting, all neighbors contribute equally. However, the proximity of the neighbors can be considered during the voting, because the closest neighbors indicate the class of the object more reliably, especially when the nearest neighbors vary widely in their distances. This is known as weighted k-nearest neighbors algorithm, where neighbors are given some weight value. For example, weighted values can be in terms of the inverse of their distances. Let's consider this diagram. For example, we consider 4 nearest neighbors, and the class of X is unidentifiable, since we have 2 blue versus 2 green. And as a solution, we can employ weighted k-nearest neighbors. Now, suppose the 4 closest neighbors have the following distances: 0.025 of green class, 0.026 of blue class, 0.035 of blue class, and 0.065 of green class. First, we find the inverse of distances, so we have 40 for green class, 38.4 for blue class, 28.6 for blue class, and 15.4 for green class. And next, we normalize the weights. So first we find the sum of inverse distances, which will give us 122.4, and then we find weighted values, which will give us 0.31 for blue class and 0.23 for blue class, and 0.33 and 0.13 for green class. Lastly, by summing up the scores for each class, we obtain 0.46 for green class and 0.54 for blue class. Since the blue score is higher, X sample will be assigned to blue class. Now, we have covered number of nearest neighbors k, and now let's cover commonly used distance metrics in KNN. The most popular distance matrix is Minkowski distance, especially two cases of it, Euclidean and Manhattan. Here we can see the formula which is used for Minkowski distance. Euclidean is a case of Minkowski distance with the p equal to 2. And Manhattan distance is a case of Minkowski distance with p equal to 1. Euclidean metric is a metric that estimates the straight distance between the points in a plane. Manhattan metric is a metric that estimates the distance between data points in the grid-like path. It is also called a taxicab distance or city block. Another commonly distance metric is Mahalanobis distance. It measures the distance between the data point and distribution in terms of standard deviation. Euclidean distance works well for any multidimensional data, only if all the features are equally weighted. For data where each feature has different weight on the data classification, Mahalanobis distance is preferred. The difference from the Euclidean distance is inverse covariance matrix. And the role of inverse covariance matrix is the estimation of standard deviation of the data point from the mean. Well, we have mentioned that KNN is a supervised learning algorithm which is used to solve both classification problems and regression problems. In classification problems, the output is a discrete value that is the most frequent among the closest neighbors. So, an example of KNN application in classification problems is classification whether the person is eligible for credit loan based on some parameters or not. And in regression problems, the output is continuous value, which is the mean value of the closest neighbors. An example application is prediction of the temperature based on the humidity and wind speed. KNN is a lazy learner. There is no training in KNN, and it doesn't learn a particular function from the training data but memorizes the training dataset instead. But the prediction step in KNN is relatively expensive. To make prediction, KNN searches for the nearest neighbors in the entire training set. And one of the ways that can be used to speed up KNN is KD tree. We have covered KNN, and to get better intuition of it, let's get introduced to decision boundaries and Voronoi diagram. Decision boundary is a hypersurface that is used to partition the underlying vector space into two sets, one for each class. And Voronoi diagram partitions the given space into regions with decision boundaries determined by distances to specified class objects. Example of application of Voronoi diagram is searching for the closest supermarket or hospital to a specific location. And other applications are epidemiology, weather, geophysics, etc. On this diagram, k=1 case is used to split the diagram to blue and red regions. Now let's cover some elements of Voronoi diagram. The first one is Voronoi cell, which is bounded by the edges. Voronoi edges are a set of points on the line that are equidistant from the two sample points. And Voronoi vertices are the points where three or more Voronoi edges cross.